Today we're going to talk about the chain rule for functions of more than one variable. And I've broken it up into two parts, a single independent variable, and then down here, two or more independent variables. So let's start with a single independent variable. Here's a typical setup. We've got W, which is the dependent variable up at the top here. And W, we can see, is a function of X, Y, and Z. Those are the intermediate variables. X, Y, and Z, in turn, are functions of T. So T is the independent variable. And you can use a tree like this to help you write down the chain rule for your specific problem. So what you're going to do is multiply down each branch and then add up the results. So in this case, you'll be adding three separate products. So let's just start. Let me erase this mess. dw dt. I start up here, del w, del x, and I multiply by dx dt. That takes care of the first branch. Now I do the second branch. Del w, del y, dy dt. And then finally, del w, del z times dz dt. So you might be wondering why sometimes I'm using a del and sometimes I'm using a d in this formula. And the rule is right here in this box. If you're at any given variable and below you is more than one variable, so for example, if I'm at W, below me there's an X, Y, and a Z, those derivatives are partial derivatives. If you're at a variable like X and there's only one variable below you, then that's a regular derivative. Okay, so let's try this out. I want to draw a tree for this first one. So part A, I can see that W is a function of X and Y. So W is going to go at the top, X and Y go beneath W. And then reading further, I can see X is a function of T and Y is a function of T. So we've got a T here and a T here. And the tree is only to help you do part B, which is to write down a general formula for dw dt. If you can do that without a tree, that's fine. So dw dt is del W, del X, dx dt. So what I did is I multiplied down this first branch, and you don't have to label the derivatives over each branch if you don't want to. So this is del W, del X here, but just the tree alone is enough to remind you of what you're doing. And then you can add on del W, del Y, dy dt. That's the second branch. Okay, part B is very important because it's going to help you do part C. So part C is to find dw dt for our specific problem. And it's very helpful to have the general formula written down in front of you to guide you as you go, because there can be a lot of terms and a lot of variables going on when you do these problems. So dw dt is partial derivative of w with respect to x is 2xy, and then I multiply by dx dt, which is negative sine t. And then I'm going to add on the partial of w with respect to y, which is x squared, and multiply by dy dt, which is cosine t. Okay, now we want to write that all in terms of t. So I can see I have three variables here, an x, y, and a t. I want to rewrite that in terms of t. How do I do that? Well, back substitute. We know x is cosine t, and we know y is sine t. So this is 2 cosine t sine t times negative sine t plus cosine squared t times cosine t. And finally, that's negative 2 cos t sine squared t plus cosine cubed t. Okay, let's do another one. Perhaps you should pause and try and do this one on your own. All right, so let's start with a tree. We want W at the top, and I can see W is a function of X, Y, and Z. And X, Y, and Z I can see are all functions of S, right? And so for part B, I want a general formula for dw ds. So I'm going to multiply down each branch and then add. So I want partial of W with respect to X, and then dx ds, a partial of W with respect to Y, dy ds, and finally del W, del Z, dz ds. All right, and for our specific problem, the functions we have, dw ds is, all right, I want the partial of W with respect to X. That's Y sine inverse of Z. multiply by dx ds, which is 3 e to the 3s, and then add on partial of w with respect to y, which is x sine inverse of z. dy ds is 3, and then del w del z is x y over the square root of 1 minus z squared. Then I multiply by dz ds, which is 3s squared. Okay, now we do cleanup. I'm going to write this all in terms of s. That's the independent variable. So I need to back substitute x is e to the 3s, and y is 3s, and z is s cubed. So this gives me 3s sine inverse of s cubed times 3 e to the 3s plus e to the 3s times sine inverse of s cubed times 3. And then finally, the last term, xy, is 3s e to the 3s over the square root of 1 minus z squared is s to the 6th, and multiply by dz ds, which is 3s squared. Okay, all together now, that's 9s e to the 3s sine inverse of s cubed plus 3 e to the 3s sine inverse of s cubed plus 9s cubed e to the 3s over the square root of 1 minus s to the 6th. All right, if you have two or more independent variables, the idea is the same, except that you're going to have a separate derivative formula for each independent variable. So in my example here, I've got w at the top, intermediate variables are x and y, and I've got two independent variables, r and s. So I have a formula over here for del w del r and a formula for del w del s. And the way I get the formula for del w del r, for instance, is I only go down the branches that end in an r. So this one and then this one. Multiply along each branch and then I add. Same idea for del w del s, only go down the branches that end in an s. All right, so let's give it a try. Here we've got a function z, and it's a function of x and y. So I've got z at the top, I'm making a tree here, so this is part A. Z at the top, and then I have an x and a y, and then I see x and y are functions of s and t. And you might say, well, the formula for x has no s in it, but the formula for y does, so you're just going to put a s and a t underneath each one. So s, t, s, t. All right, there's my tree. Now I want a general formula for, in this case, del z del t. I could do del z del s, but I'm going to do just del z del t to show you how it works. And it's actually almost easier with two or more independent variables because everything's a del, there are no d's. So del z del t is, I'm only going to go down the branches that end in a t. So del z del x del t, and then I add on del z del y del t. All right, and for our specific problem, del z del t will be the partial of z with respect to x is x over the square root of x squared plus y cubed. Now I did that sort of quickly, so let me show you in my scrap paper over here what happened. I'm going to write z as x squared plus y cubed to the 1/2. And when I take the partial with respect to x, I bring the 1/2 down, I leave the inside fixed, subtract 1 from the exponent, and then I multiply by the derivative of the inside with respect to x, which is 2x. So this 2 is canceling with the 1/2, x is on top, and the negative 1/2 exponent here is giving me that square root sign that I see over here in the bottom. All right, and del x del t is 2t. Then I add on del z del y, same idea, except now we take partial with respect to y. The 2's won't cancel. On top, I'll have 3y squared, and downstairs I'm going to have 2 square root of x squared plus y cubed. Pause the video, make sure you follow that. And then del y del t is simply s. Okay, now I want to write that all in terms of s and t. So I back substitute, x is t squared, and then I have square root of t to the 4th plus s cubed t cubed times 2t, and then 3y squared is 3s squared t squared, and then that's over twice the square root of t to the fourth plus s cubed t cubed, and that's times s. And so finally, we get 2t cubed over square root t to the fourth plus s cubed t cubed plus 3s cubed t squared over twice the square root of t to the fourth plus s cubed t cubed. All right, we're going to do one more. I'm just going to get you started and you're going to finish it. Here we've got a function z of x and y. So z is at the top, and then I have an x and a y, and I can see that x and y are functions of u and v. All right, let's write down a general formula for del z del u. That's del z del x del u plus del z del y del u. You can see why there's no one single chain rule. For each problem, it's different. And so if you learn the process with the tree and multiplying down the branches, then you can pretty much do the chain rule for any specific problem. Okay, and then let's go a little bit further. Del z del x is 4e to the x ln del x del u. So I want the partial of log u cos v with respect to u. So I put the derivative on the top with respect to u, which is cosine v. And in the bottom, I put the argument, which is u times cosine v. So those cosine v's actually are going to cancel. And then I add on del z del y, which is 4e to the x over y. And then del y del u, well, y is just a function of v, so del y del u is 0. So that whole term is going to drop off. Now what you're going to do is back substitute. X is ln u cos v and y is sine v, and you can show the last part that simplifies to that function you see there. Okay, this example here that you see at the end is just showing you that suppose you want to find a partial derivative at a single point using the chain rule. I've started us out here. You've got w, which is a function of x and y, and p and q are the independent variables. You can stop right at this intermediate point. So here I have del w del p in terms of x, y, p, and q. Normally I'd have to back substitute x and y in terms of p and q. However, I can stop here because I know what p and q are. That's up here. And so when p is 0 and q is 1, I can just find x and y by hand using these formulas. That's what I did here. And then plug those 4 values in. 4 values. And so it's just a little bit shorter. I mean, you could do it going all the way to p and q and then substitute, but this just saves you one step. All right, and finally, we've got implicit partial differentiation, and I've got a couple formulas for you there and 2 solved examples. All right, and that is the end of this section.